Okay.
Recording in progress.
Punch card badge promises.
All that stuff. Thank you, everyone, for coming. It's my pleasure to introduce you to Steve. I don't think I have to introduce you. Actually, I didn't know your career, so I checked online and I didn't know. Steve was former professional football player playing as fullback on Miami Dolphins, and it was also in the NFL. Steve is 6'2" and a weight on shape of 227 pounds, and then somehow he switched to astronomy after a beautiful career.
That's slimming down.
Yeah, a little bit. I see that. I mean, your last match was in, what is it? Well, I got it in, I think it was something like 1983. So it's like 40 years after, you still pretty fit. So after all this NFL career, Steve is a double master in astronomy and physics. He got his PhD in the University of Amsterdam. And then he moved to the University of Wyoming and University of California, and until he landed in NASA, where you became the head scientist or the project scientist of Kepler and K2 missions. And now you work at the Ames Research Center. Mm-hmm. And it's, as maybe people from Gemini may know, that is also an expert in spectral imaging. And you may be familiar with two instruments that are really spectacular, that are Alopec and Zorro, one at Gemini North, one Gemini South. And today we'll talk about what we can learn using almost diffraction limited imaging with a emitter telescope.
Great, thank you. Okay. Yeah, I was also the lead guitar player for the band Yes years ago as well. All right, so thanks for having me here and talk. And this is so relevant to Gemini North because we did all this work here with Alopec and all of your lovely great seeing and telescope help and stuff like that. So we're going to talk about two stars, Betelgeuse and Siwarha. Siwarha is the new name for the newly found companion. This image here is an image that came from the Noir Labs press release. So it's kind of a beautiful picture compared to what we actually saw. So I'm going to talk a little bit about a few things today. I'm going to give you a little history about the constellation of Orion and the star Betelgeuse. Then I'm going to give you a very brief primer about speckle interferometry for those of you that don't know about it. And for those of you that don't know about it, I've heard from Andy, you're going to be immediately fired from Noir Labs for not knowing about speckle imaging. Go away, know that. And then we're going to talk about the Betelgeuse itself and the companion. So just some facts about Betelgeuse that are relevant later, the ones sort of highlighted here. It's a red supergiant. It's the closest red supergiant to the Earth, although Antares is almost the same distance, and in fact, almost the same angular size, almost the same everything. It's almost a twin, and it has a companion as well. But anyway, Betelgeuse is only 10 million years old, the baby little star. It's massive. It has a pulsational period of about 400 days, and all big stars tend to have pulsational periods. But it also has this long secondary period, it's called. And there's been arguments for over 100 years about the cause of this long secondary period, which is about 2,000 days. Some people believe that 2,000 days could be a pulsation period of Betelgeuse, and that the 416 was some harmonic of that, but Betelgeuse would have to be about 10 times its size to have its pulsation period be 2,000 days. And that doesn't agree with its angular size and its known distance. So that's been kind of a mystery, and we'll get into that mystery a little bit. Betelgeuse also has a faster rotation rate than it should for being a red supergiant. We all know that as stars get older and they expand, they slow down in their rotation rate, kind of the ice skater analogy. And so Betelgeuse should be rotating slower. So it's another aspect that for a number of decades has been thought to mean that there's a companion that spins up Betelgeuse. So people have thought about this for at least 100 years. So in Greek mythology, we all probably know this figure. This is the hunter, right? Orion, the hunter. And Betelgeuse is the star at the shoulder of the hunter. And it doesn't matter which view you use here, hunter facing you, hunter facing away from you. Betelgeuse is at the shoulder, and the three stars of the belt, very familiar and common to us. But in Arabic astronomy, this is the constellation that we call Orion. This constellation was called Al-Jawah, and in this constellation, Betelgeuse is the hand holding the bow. So it's not the shoulder, it's actually the hand of the hunter. And I like this one so much better than Orion. Orion's this old white Greek guy who looks mean, and this looks like some great person having fun shooting arrows and has little treasure purses with them and stuff like that. So I like this much better. And again, keep in mind that Betelgeuse here is the hand of the giant, not the shoulder of the giant. So just comparing the two to keep this in your brain: shoulder, hand, same constellation, just two different aspects of it. So I'm going to move now to a little bit of history of Betelgeuse and this idea of the companion. So on the right side here is a drawing from a 2004 paper of the star Z Eridani, which is also a red supergiant, also suspected of having a companion that orbits at the long secondary period of that star. Many, many red supergiants have long secondary periods, and many, many red supergiants are therefore believed to be binaries. This shouldn't really surprise anybody because red supergiants come from very massive stars. And almost everybody in astronomy would believe that most massive stars are binaries. And so one of them evolves a little faster than the other. It becomes a red supergiant. The other star is just kind of stuck with it and tends to orbit very close to it, or in fact, even in its upper atmosphere, because the star gets very big. So this shouldn't be a surprise. There's records of Betelgeuse for tens of thousands of years in humankind, not great records for that long, but records of it. But there's really good records of Betelgeuse for over 100 years. People have been watching the star, taking spectra of the star, trying to do astrometric measurements of the star for many, many, many years. And we'll get into what those records, if you take them all together, have shown us for all that time. The long secondary period was first noted in the early 1900s and suggested as a spectroscopic binary, but nobody ever could find the star for various reasons. The reasons mostly are that Betelgeuse is really bright and the star is really close to Betelgeuse. It was believed to be something between 10 and 40 milliarc seconds of separation. So for those of you that don't know what a milliarc second is, get your little protractor out, go stand out in the quad, look up at the sky, look at a degree, and then imagine dividing it and dividing it and dividing it. It's a pretty tiny little distance. Or think of the average seeing, even at a great telescope like Gemini, of something like 0.4 or 0.5 arc seconds, just a tiny little separation. I mentioned the fast rotation rate. Its rotation rate is 5 kilometers per second, which is pretty fast. And in the 1990s and 2000s, the long secondary periods kind of came back in favor as being companions. And that was mostly driven by the Macho survey. The Macho survey, if you might remember or know about it, it looked at the galactic bulge for microlensing events, but they found thousands of variable stars. And many of those were red supergiants, these things called yellow hypergiants, all these things that are kind of in the top right corner of the HR diagram, these big evolved stars. And something like 80% of them have long secondary periods. So it became kind of back in favor. And if you're going to study any red supergiant, you go to Betelgeuse because it's the closest and the brightest and all that kind of stuff. So what started this particular research project was in the fall of 2024 and early into the very beginning of January of 2025. There were two very large papers published in the literature. And by large, these are like 35 or 40 page papers. So one, think of the cost of that. It's like, wow, that's like crazy to pay for that. But these papers were done by two independent groups. They were both about Betelgeuse, and they both basically came to the same conclusion in slightly different ways, using not just the same data, but using pieces of the same data in different ones. So the first paper I want to talk about is Goldberg. And Goldberg started out with the premise that many red supergiants have long secondary periods. So that was known, that it was sort of revised and brought back to light in the early 2000s. And they said, okay, if we do that, and we know Betelgeuse has a long secondary period, what can we learn from studying all the stars that have them? So they looked at these light curves I show here in the picture. They used V-band photometry from the AAVSO and photometry before that from the Harvard Plate Collection. And that's in the top plot here as the blue dots, the blue points. And then they used radial velocity data that's been taken by a number of telescopes around the world for many, many decades. And that's the bottom plot here of, again, the blue dots. So you can see a couple things there in these quite strikingly obvious things here. in both plots, you see this much more rapid dipping, and that's the 416-day pulsation period of Betelgeuse. The red line here is the long secondary period drawn on top. It's a little more obvious in the radial velocity curve. You can see how the red dotted line kind of follows the radial velocity curve quite well. It's a little less obvious in the photometry, just because Betelgeuse has a lot of very large convective cells. Those convective cells can really mess with the perfect photometry over time. But you can see mostly it kind of fits there as well. So this was their conclusion of this study, was that the long secondary period is clearly real, and the long secondary period in the radial velocities really points to there being a companion. There's something else there. It's like finding a planet signature around a star. There's something else there. So they came up with this empirical model. These are the same data in kind of gray now, and then the blue line is now a phased period of the long secondary period. And in the middle, it shows you the eyeball view of where this companion star would be at each of these parts of the phase. And when you'd want to look at this companion star are the phases where the companion star is the most separated from Betelgeuse. That's the only chance you have. If it's in front of Betelgeuse or behind Betelgeuse, you won't see it. So this gave predictions of when the best time to look would be. And remember, this paper came out in the fall of 2024, and magically, early December of that year was when the companion was going to have its widest separation. So a few months after the paper came out, there was a chance to have its widest separation. And they made some predictions about the companion based on the radial velocity amplitudes, that the companion would be something like 1 solar mass, a little bit, assuming the inclination was near the equatorial plane of Betelgeuse, which they also concluded from their work, that it might have a temperature of 6,000 to 7,000 degrees Kelvin. And that was solely based on the fact that its mass would be a little warmer or a little more than the sun. So they never had any temperature measurements. They just said, well, if it's a star and it's a little more massive than the sun, that'll roughly be its temperature. They predicted that the maximum separation would be 52 milliarc seconds, and its delta magnitude, so how much fainter it would be than Betelgeuse itself, would be between 6 and 10 magnitudes. So that's pretty faint compared to Betelgeuse. And as I mentioned, the maximum separation was a few months later. So that's got me thinking about Gemini and our instrument. Maybe we could do something. And then this other paper came out just a little after that, and they used 100 years of data. The other paper only used about 50. This used 100 years of data. And you see the same thing here. The radial velocity curves are those black lines, radial velocity points. And then the blue kind of shaded thing is this long secondary period phased on top of that. Again, the same conclusion was this must be a companion star. They came up with slightly different parameters, though, for the companion. In this case, they said it's going to be 10 to 15 magnitudes fainter. That's really challenging. And they said that its temperature would be roughly that of Betelgeuse itself. So it would be 3,000 or 4,000 degrees Kelvin. And in this case, they predicted that temperature because they knew that its orbital period and separation would have the companion orbiting inside the chromosphere of Betelgeuse. And therefore, they thought that its temperature would basically have equilibrated to the temperature of Betelgeuse itself. And they concluded also here that the orbit is likely to be edge-on, that is, in the equatorial plane of the star Betelgeuse, which is known very well, by the way. The rotation angle of Betelgeuse is known. They took the radial velocity data, also phased it on that period. You can see it phases very beautifully here. It's a lovely radial velocity curve, assuming you have all this data, 100 years of data. It really helps. And their predictions here, again, the temperature could be as cool as 4,000. It's nearly edge on, about 98 degrees. And they said in this paper that the prospect of anybody directly imaging this would be essentially zero. Well, those two papers got me thinking, and anybody that says you can't do something in astronomy makes me think we should try to do something in astronomy because it's pretty fun to do. And 52 milliarc seconds, if you think about the diffraction limit of the Gemini telescope, is huge, right? It's like 4 times the diffraction limit, right? So it should be cake for us to do it, right? Trivial. Anyway, challenging measurement. So I'm going to take a little aside here. The aside is that in 2019 to 2020, there was this event called the Great Dimming Event. And people predicted, or some people predicted, that this meant Betelgeuse was expanding wildly and was going to blow up and be a supernova. And some of us, including me, thought, wouldn't that be cool? But it turned out to not be true. Betelgeuse had a large mass ejection that happened to be pointed right toward the Earth. And that mass ejection, as the material came out from Betelgeuse, it cooled very quickly, turned to dust, blocked the light from Betelgeuse. And these are 4 images of Betelgeuse from the VLT that show this event happening. And you can see in the 3rd frame here in January 2020, Betelgeuse is kind of blocked by this sort of cloud. And then in the end, it kind of comes back to being bright. So this was not a precursor about anything about a supernova. It also had nothing to do with the fact that Betelgeuse has a companion. There's still some people that believe that the companion might be the cause of pulling mass off of Betelgeuse. But the companion's only about a solar mass. Betelgeuse is 18 solar masses, so it seems like it's probably unlikely that it affects it all that much. So that's just an aside. There were also, after these papers came out, the people that had written the papers, of course, they knew the papers were going to be published, so they had applied for director's time with the Hubble Space Telescope and with Chandra, believing that surely these famous, expensive NASA telescopes in space would find the companion for us. So they searched with Hubble, and we'll talk about it a little bit more in the next couple of slides. They searched with Hubble in a way that seemed to me kind of doomed from the start, but it's the way that they knew. So they used a high-resolution shell spectrograph. They could not point directly at Betelgeuse because it's too bright. So they pointed at 4 quadrants around Betelgeuse, looking at the scattered light from Betelgeuse, and assumed or hoped that in one of those spectra, they would see some feature that was different than the other features. And that feature would be due to this companion star in the atmosphere of Betelgeuse. And by this time, they knew which quadrant the companion should be in. So they did this, the paper's published, the data looked pretty crappy because it's scattered light and they saw nothing. Absolutely nothing was seen that didn't look just like Betelgeuse or noise. The other search was a smaller type of search where Chandra stared close to Betelgeuse. Again, it can't look right at Betelgeuse. And they looked for X-rays, additional X-rays from Betelgeuse, because one of the papers that I mentioned before predicted that the companion might be a neutron star. And if a neutron star was plowing through the atmosphere of Betelgeuse, there should be a lot of X-ray emission. Well, no X-ray emission was found. So these 2 things made an attempt to find some evidence of the companion, but nothing was found. So the Space Telescope thing that I mentioned, here's a map they put in their paper. So there's these 4 quadrants. So Betelgeuse is the dot in the middle there with the cross on it. And these are 4 quadrants where they looked and took spectra of, hoping that in the eastern quadrant, that arrow points to where the companion should be. In the eastern quadrant, they hoped they would see some additional signature, something different in the spectrum, but they didn't. The errors box over there is proposals to try to get a spectrum of Betelgeuse's chromosphere that Tom Ayers did a long time ago. And again, he couldn't look at Betelgeuse, so he looked offset and got spectra of the scattered chromospheric light to do the work on that. So it's really difficult to look right at Betelgeuse. It's bright, everything saturates. So in this picture, the axis with the little spin on it that's just above the letter S, that's the rotation axis of Betelgeuse. And so the orbital plane of the companion is thought to be very close to the equatorial plane of Betelgeuse. And again, the arrow there in the east thing points to where the companion was supposed to be predicted to be based on those papers. So the prospects of direct imaging being near zero, of course, made me think that if anybody can do it, we can, right? Because we clearly have an instrument that's really suited for this, better than doing spectroscopy or better than doing X-rays. But Betelgeuse is very bright. Gemini is a really big telescope. So could we stare right at Betelgeuse? It turns out the answer is yes. And we've actually done this 3 times now. And I'll tell you, the first time we did it, we were kind of lucky. But the second time we knew what we were doing. So that was good. It's a challenging observation, right? We had to find something very close to Betelgeuse that's so much fainter than Betelgeuse. So we observed it once in February of 2020. And if you remember what I talked about, the great dimming a few slides ago, that was during the great dimming. So Betelgeuse in the optical was 1.5 magnitudes fainter than it normally is. So that helped us out a little bit. And it meant that at 562 nanometers, we could roughly observe it like we observed most of our targets, and it didn't saturate. However, the 832 nanometer image was completely saturated, even at the great dimming. Betelgeuse is incredibly red. If you don't know that, you look up at the sky, it's very red. It's very, very red, and it really zooms up in the optical. In December 2024, when we wanted to look at it, because that was the time of the greatest possible separation of the companion, Betelgeuse was no longer dimmed. Betelgeuse was back to its regular magnitude. It has an I magnitude of minus 2.45, so that's pretty bright. Its V magnitude is 0.5 and its B magnitude is 2.5. So if you look at those magnitudes, it's a very steep gradient. But if you remember, one of the predictions of the companion was that the companion would be relatively hot. And so looking in the blue might be a pretty good thing to do. Looking in the red is just impossible. It's just too bright. So in this particular observation in December 2024, we looked at 466 nanometers, so even bluer than before. We took 10 millisecond exposures instead of 60 that we did before. And in the red channel, we just pointed to nothing because it was just going to saturate the camera. So there's no point even looking at it. Our instrument, by the way, takes 2 channels simultaneously. So we couldn't not do the red, but we just pointed to nothing. And the data reduction, we split it into 2 halves, reduced each one to see if they gave us the same answer. And you'll see what we got. What did we find? But first, we'll look at this. All right, so this is a light curve of Betelgeuse. The top is V magnitudes. The bottom is B magnitudes. This is from the AAVSO, covers the years 2017 to 2025. You see that big dip in the middle there? That's the great dimming when Betelgeuse got fainter. And that's where the line of our first visit was in February of 2020. And the reason we looked at Betelgeuse then was we wanted to see if Betelgeuse was actually bigger. Betelgeuse is 40 milliarc seconds in size, the star, so it's easily resolvable with Gemini. And so if you looked at it then and the star had actually become bigger, we would notice that. So we wanted to look at it, and we did. And then the second visit was the visit at the far right there when we were looking for the companion after those papers came out, and you can see Betelgeuse is back to its regular value. You can also notice in this plot the 460-day pulsation period. You can see these up and down dips. And if you look at it even more in detail, you can see this big sine wave that kind of goes through it. That's the long secondary period. And so it's really quite obvious in the data that that period has existed and is quite well known. So now we're going to take a little diversion again. We're going to talk a little bit about speckle interferometry in case you don't know what it is. So these are representative images of speckle interferometry. On the left side is what each of our images looks like. It looks like a bunch of speckles, hence the name. In the middle is an image you would get if you integrated on some star, not Betelgeuse because it's too bright, you'd saturate, but just integrate on some star with some usual typical telescope. And what you get in that case is you get a blob that's maybe an arc second across or something like that, sort of a seeing limited image. And on the right is what this star really is. This star is really a close pair of stars that get blurred out by the atmosphere. But if you take all that speckle data, you apply Fourier techniques to it, you can reconstruct that image to what you would have seen if the atmosphere was all gone. So you get to the diffraction limit of your telescope. At 466 nanometers, the diffraction limit of Gemini is about 14 milliarc seconds. That's about 1 pixel in our plate scale for our imager. But that's about 4 or 5 pixels for the separation between Betelgeuse and its companion. So if it's there and it was bright enough, we should easily find it. So here's how it works. You take a power spectrum of a single star, this thing up here with the cross. You get the image on the bottom when you reconstruct it, a single star. Very exciting, right? Power spectrum, single star, it gives you a single star. However, if your star is really a binary or a triple system or has jets or other features that you can measure, you get a fringe pattern. That's the interferometry part. And if you take that fringe pattern and reconstruct that image to what it would have looked like to make that fringe pattern, in this case, you get this thing on the bottom, right? Two stars very close together. These two are separated by 0.16 arc seconds. They're roughly equal brightness, so about a magnitude apart, and that's what you would get from it. So this is what you do, and in this case, the fringes are bright, they're very obvious. These stars are not very different in magnitude, so this is kind of a lovely ideal case. Remember, Betelgeuse, the companion was supposed to be 6 or 10 magnitudes fainter, right? So that means the fringes are going to be very low signal noise, if they're even there at all. Okay, so let's look at our February 2020 data. So this is an image of Betelgeuse that's been reconstructed. The size there is the resolved star. So it's about 41 milliarc seconds across. You can actually resolve the star. And the angular diameter here was the same as the angular diameter of Betelgeuse has always been. Therefore, during the great dimming, Betelgeuse got no bigger. So we looked at this, we said it's no bigger. We didn't think this was really worth publishing just that because other people had looked with other techniques like the VLA and stuff, or the LBT. And so they saw that it wasn't bigger. So we just kind of moved on with our life. But it showed that the star wasn't bigger. The dimming wasn't associated with the star being bigger. The supernova wasn't going to happen quickly. And of course, there was no companion detected here. And when we went back and looked at this after the image I'll show you next, we said, oh, isn't that weird? We didn't detect a companion here. But at this time, the companion would have been behind the star. So we wouldn't have seen it. We didn't see it, so that's very exciting. This is how we measure angular diameters. This is the angular diameter. On the left here is the angular diameter in February 2020. On the right is the angular diameter of Betelgeuse we measured in December of 2024 when we were searching for the companion. We wanted to just show that the star is the same size then. It's been 4 years later, but it's still the same star. It's still the same size. So we showed the angular diameter hasn't changed. Betelgeuse is still Betelgeuse, but could we find the companion? Finally, the money slide. So here's the companion. We found the companion in December of 2024. It's the thing the yellow arrow is pointing to. The image on the left here is the February 2020 image during the Great Dimming. No companion seen. The image on the right is the December 2024 image. You can see the companion there is that not point source thing. It's actually got some angular size to it. It's not a dot like a star should be. The top right corner of that, the inset there, shows what a non-resolved point source would look like. And you can see that the companion is bigger than a non-resolved point source. And so at first that was kind of, what? But I'll explain it in a moment. You also notice that there's a ghost image of the companion. So in interferometry, you can always get this 180-degree ghost. And we use a technique that allows us to know which of those ghost images is the real one compared to which one's the fake one. And in this case, the real one was the bottom left one here. And you might remember that position seems awfully like the position where it was predicted to be. Now, we did reduce this data before we knew where the predicted position was. So this was where we said it was. One of those papers said it's right there. Looks like a pretty good match. And so we found that its separation was 53 milliarc seconds, basically what was suggested. It lied in the equatorial plane of Betelgeuse, as was predicted and suggested. And it was the right delta magnitude, in this case, at about 6 magnitudes fainter than Betelgeuse, so in the range of what was predicted. So the name of the star was called Siwarha, which means in Arabic, her bracelet. So if you remember in Arabic, Betelgeuse was the hand, not the shoulder. And so we went back and called it something cool compared to Arabic and kind of gave up on the Greek stuff. All right, so a recent paper has come out, which we talked about a little bit in our paper, saying if the star orbits in the chromosphere of Betelgeuse, it's probably surrounded by some ionized gas, and that's why it's probably not a point source. And that's why we saw it as some extended image. So we just kind of said that in our paper. This paper came out recently by Andre Dupree, which looks at about 30 years of spectra from Hubble and some ground-based telescopes. Mostly spectra in the ultraviolet are very blue. And from that, you can look and find that there are shock waves that go around in the atmosphere of Betelgeuse with a period of about 2,000 days. They basically are the bow shock that follows this star around as it orbits inside Betelgeuse's atmosphere. So that gave us also more faith that we're not going to see a point source. We're going to see something that sort of has an ionized cloud around it as it goes around the atmosphere. So we make contrast plots to tell what we can see and what we can't see. And these contrast plots look at separation in arc seconds from Betelgeuse being at 0, and then how much away from Betelgeuse in separation of arc seconds could you find things. And then on the y-axis here is what's the contrast in magnitudes of things you should be able to see. So the red dashed line here is the contrast curve we got from our February 2020 observation, which shows that if the companion was there, we would have seen it, and we didn't. The blue line shows our contrast curve from the December observation, which shows that if the companion was there, we should see it, and we did. The companion has pretty big error bars because this is a very low significance signal noise detection. It was only a sigma of 1.5, and normally we like things to be like 5 sigma to believe them. But because of all this other ancillary information of the right separation, the right place, the right orbital plane, all that, I think it's a pretty good detection, but very, very at the edge of what we can do. So here we've made a really highly stretched image because we wanted to try to get the astrometry of the star. And of course, the star, as I mentioned, is not a single point. It's sort of a fuzzy thing. So we just looked here to make sure we knew exactly the center of the light and the orbital period and the separation. Those, of course, all agreed with the parameters that the models predicted and the position where it was predicted. And it's about 6 magnitudes fainter, but that's plus or minus about 1 magnitude. So it's pretty uncertain what the delta magnitude actually is. If we take an isochrone for a 10 million year star, Betelgeuse is the red dot. You can see Betelgeuse is cool. Betelgeuse has a very high absolute magnitude. The blue box is the range of where that plus or minus 1 magnitude star could be. It's a little warmer. Its absolute magnitude's a little lower, right? And those are 6 magnitudes apart. Look at that. Magically, it all works out. Mm-hmm. Right? So we predict that the thing we see, the kind of ionized envelope we see around the companion is about 7,000 degrees Kelvin. And its mass is maybe 1.5 times the mass of the sun. Again, kind of based on this isochrone and based on our delta magnitudes with error bars, right? Of course, with error bars on those. All right, so here you guys are the first to see this, breaking news. So Betelgeuse was observed again in December 2025. So this was just a few months ago. Oh, this is January, last month. Sorry, this last month. At 466 nanometers again with 10 millisecond exposures. At that time, based on the orbital parameters of the secondary and based on our first measurement, we predicted that the star would have a position angle of about 115 degrees if it's in the equatorial plane, if it stayed in the equatorial plane, and it would be 34.5 milliarc seconds from the center of Betelgeuse. Betelgeuse's radius, its angular radius, is 20 milliarc seconds. So the star will be about 14 milliarc seconds away from the edge of Betelgeuse. If you remember many slides ago, we talked about what the resolution is at 466. 1 pixel is about 14 milliarc seconds. So the question is, could we detect something 1 pixel off the limb of Betelgeuse that would be the secondary companion as it moves to go behind the star? Well, I would not publish this yet in a paper, but maybe when we observe it next year or the year after. So let's look a little bit at the setup here. So here's a blow up of the scene around Betelgeuse. So Betelgeuse is the big red ball. The black line at a horizontal or a vertical there tilted over is the rotation axis. The other black line is the equatorial plane of Betelgeuse, which is supposedly the equatorial plane of the orbit of the companion. Its uncertainty is plus or minus 15 degrees. Our uncertainty is plus or minus about 12 degrees. So our orbital plane, which is the red line, and the equatorial plane of Betelgeuse to me are kind of the same because their errors overlap. The kind of brownish circle at the end of the arrow is where Siwarha was seen in December of 2024. It's the first observation I showed you when it was the widest separation. The black triangle is the predicted position in December 2025, sitting 1 pixel away from the edge of Betelgeuse. So we thought, why not try it? Here's the observation. If you look on the left, you might not believe anything that the arrow is pointing to. You say, it's Betelgeuse. Doesn't quite look round, but you know where it's bulging is kind of right where that arrow is, right? On the right, I've taken this image and overlaid the previous image showing the position of where Siwarha was predicted to be. And you can see that triangle falls right on that elongated pixel. So I wouldn't go to press with this, but I think it's somewhat intriguing that this looks like maybe we saw it again just before it disappeared behind Betelgeuse. So in about a year and a half, it should be on the other side. And so we'll look at it again and see if we find it. So here's the conclusions I have, that I think Alipaki and Gemini, for the first time in 100 years, actually directly imaged the companion to Betelgeuse. The great dimming event was not a precursor to a supernova or caused by large expansion. It was just caused by mass ejection. Betelgeuse's companion being directly imaged. Will we learn anything more from more direct images of it, especially if we're not really seeing the companion, but we're seeing this ionized cloud around the companion? I don't know. Can we do it in any other colors with very blue? Probably not. We talked about why the companion's called Siwarha, as it's the bracelet. Maybe we detected it a second time. Maybe, I don't know. And we'll re-observe Betelgeuse again in 26 and 27, and hopefully eventually we'll see it pop out on the other side. So thanks very much. I'm happy to take questions.
Questions? Yeah.
So with the speckle imaging, how do you figure out which one is the ghost image?
Yeah, there's a technique that's called bispectrum, and you basically look at the speckles on your images, and the speckles that are phased on the certain side, the phasing shows you which of the sides is real. Right? It's the part of it. So there's two parts of it. There's the power in a Fourier transform, and there's the phase of the data. So the power tells you how much light you get, and the phase tells you where that light is. And you can use that to pick which side is the real companion. We've done experiments with this with better data than that. We bettered where the companion wasn't so faint. And in maybe 98% of the cases, compared to observations that other people can make where you can actually directly image the stars, we've been correct. So we feel like it's pretty robust technique.
Right, thank you.
Sure. This question?
Yeah.
Yeah.
So if the companion was found to be 7,000 Kelvin, that means that that second large paper was wrong in speculating that it should have the same temperature as Betelgeuse photosphere. So how?
But they had a big range, if you remember.
Yes.
I think it was 4,000 to 6,000.
Okay, so wow.
And ours was, not much different than that.
Okay, so not big of a concern about that.
I'm not concerned about that. In fact, if you remember the plot here, you can see what our temperature uncertainty is, right? It's quite large. Anything else? Andy?
So you mentioned you used very, very short exposures. About how many did you need in order to detect the companion?
We took quite a lot because Betelgeuse was at low air mass, and we were trying to figure out how could we even image it. But in the end, we used only about 6,000 exposures, which is about 6 minutes of telescope time to find the companion.
So we'll look forward to that 6-minute proposal.
We can round it up to 10.
Right. Just for comparison, I think there was 12 orbits of Hubble was used in that attempt.
7 minutes.
I guess. Oh, yeah.
So the image that we've all seen has red and blue,
Oh, yeah.
but you had no red, right? So
No. That was colored by the Noir Labs.
well, that's what I thought. Just
Yeah. Yeah. They kind of looked at the temperatures and said, what's a star look like, or what's the color of a star at that temperature?
Does this experiment become easier or harder with a 30-meter telescope?
Well, the experiment in principle becomes easier because the resolution's better, but speckle imaging with a 30-meter is still a challenge, and it's obviously never been done yet, because there's a lot of atmosphere above you, right? There's a lot of cells going over. And so you're probably going to need to do something more than our simple instruments. You're probably going to need to have wavefront sensors and have a little bit more complicated data reduction processing. But in principle, with a 30 meter, you get something like 4 milliarc second resolution. Right? So a lot more fun stuff you can do.
Hi, Steve. It's Jen over the big, the big sound. So you rule out any sort of just debris disk just based on temperature and distance. Like you would assume that would all be way too close and you would not resolve it.
If Betelgeuse had a debris disk,
Yeah, that's not what you would be seeing in Alopece.
no.
Okay.
Now, I think if Betelgeuse had a debris disk, a couple of things, it'd probably be a much brighter IRAS source and much brighter in the infrared because a debris disk would probably be cooler and very infrared bright. And if it had optical brightness to it and was larger than Betelgeuse, we probably would have seen it in our image as some extension to the star.
Right. Okay. Yeah, because I know that a lot of I think you said this, but a lot of the dimming people besides the pulsation group were saying that it was just like a big asymmetric dust blob.
Right.
So, because yeah, although there's a whole thing about do red supergiants do dust versus is it only just AGB stars that do dust? But that would be too cold and that would be too close, so it wouldn't be this thing.
Absolutely. Yeah. And I love your term, the dimming people. That's great. I like that. Annie, you have a question?
Okay, well, go.
Oh, yeah.
It was a very nice talk.
Thank you.
I had a question whether there was a reason to wait for the companion to be just 1 pixel away from the
The reason was that we had observing time in December, and I just thought, why not? And kind of forgot about it until then. So, yeah, it wasn't like, let's wait till it's real close to then hope. And also, Betelgeuse is a very wintry star, right?
That's
So
true.
you want it to get up there. So you have to kind of wait a little bit anyway. Yeah. If we observe at more than about 1.5 air masses, things don't work out so well in atmospheric reconstructions.
So you need it to be low.
Yeah.
High.
Oh, high.
Yeah. Yeah. So it's another astronomy thing where the numbers are wrong from high and low.
Yeah.
Yeah, we need it to be more like that. Yeah.
John?
It might dumb question, but given Betelgeuse's eventual fate as a supernova, then what would likely happen to her briefly?
Oh, yeah. So a couple things. Betelgeuse, if it did explode as a supernova anytime soon, it would of course destroy that star on the way. But it's probably not likely to, maybe for another 100,000 years. So sorry, we'll all miss it. But this object, if you're orbiting inside, there's drag. And so it's spiraling in. And the prediction from just simple drag calculations is that in about 10,000 years, it'll spiral in and be gone. So if red supergiants were all older, then in principle, all the long secondary periods would not be there because all their companions would have already spiraled in. So it's the fact that it's a young star that we kind of win.
What's the separation of AU?
I used to know that. It's like Jupiter and the sun, so like 4 AU or something. Yeah, it's pretty close.
But does this help with the rotation speed?
It in principle, people believed it would because it's a companion, but the mass isn't enough, really. Yeah, so it doesn't quite solve that problem. If it needed to be something like 6 solar masses or something to have enough oomph to really spin up Betelgeuse. Some theorists will figure that out or something.
The diameter of Betelgeuse is 2 AU or something like that.
It's about the asteroid belt. So what's that, like 3 AU or something?
Okay, so
Yeah, so this thing orbits really
Close.
right inside the outer atmosphere. Yeah, it's pretty cool. It would not be a nice place to live. Other questions? Oh, yes.
Aside of being extremely bright and so extremely complicated, can you do absorption spectroscopy to detect the photosphere of the companion or something like that?
Well, good luck.
Yeah, thank you.
People have looked at Betelgeuse and have tons of spectra, but it's difficult even with a star that's 3 magnitudes fainter to see it as a double line binary. right? It's just that's such a contrast. And usually what happens in cases where you do see double line binaries is you have a star that's kind of reddish and a star that's kind of bluish, right? And they have different lines. In this case, though, the star in the blue is 6 magnitudes fainter. And in the red, it's going to even be much, much fainter, right, compared to Betelgeuse. I just don't think you're going to do it.
Is there any other question? People online? If not,
Great.
we can thank
Thank you.
Steve again.
Good.